Imagine a planet so vast it could swallow every other world in our solar system and still have room to spare. A place where storms rage for centuries, where auroras burn brighter than anywhere else, and where the very laws of nature seem to twist into something unrecognizable. This isn't science fiction, this is Jupiter. Even after decades of spacecraft visits and telescope observations, this gas giant guards its secrets like a cosmic vault. From its shrinking great red spot to its lopsided magnetic field, Jupiter defies explanation at every turn. Today, we're cracking open that vault. Strap in as we count down 25 of Jupiter's most baffling mysteries, each one more astonishing than the last. By the time we're done, you'll see this swirling enigma of a planet in a whole new light. And trust me, some of these will make you question everything you thought you knew about our solar system. Now let's zoom in on Jupiter's most famous feature, the Great Red Spot. This colossal storm has been churning for at least 400 years, possibly longer, making it the solar system's oldest observed weather system. Picture a hurricane so vast it could swallow Earth whole, yet instead of dying out in days or weeks, it's outlasted entire civilizations. But here's the twist, it's shrinking. Over the past century, astronomers have watched this monstrous storm contract, its once oval shape becoming more circular. Some measurements suggest it's now less than half the size it was in the late 1800s. So why hasn't it vanished? That's where things get even stranger. Unlike storms on Earth, which lose energy when they shrink, the Great Red Spot seems to be growing taller as it narrows, like a spinning top pulling itself tighter. Scientists suspect Jupiter's jet streams, those raging rivers of wind, might be feeding the storm, but no one knows exactly how. Some theories suggest heat rising from deep within the planet keeps it alive, while others propose it's merging with smaller storms, stealing their energy. One thing's certain, this isn't just a storm. It's a cosmic puzzle defying everything we know about how weather works. And as it continues to change, astronomers are racing to uncover its secrets before it transforms or disappears right before our eyes. Now let's dig deeper, literally, into one of Jupiter's most baffling secrets, its missing core. For decades, scientists assumed gas giants like Jupiter had a solid, dense core at their center, a remnant from their formation. But when NASA's Juno mission peered beneath Jupiter's swirling clouds, it found something startling. Instead of a compact, Earth-like core, the data revealed a diffuse, partially dissolved mess, what some researchers call a fuzzy core. Imagine expecting a rock at the bottom of a pond and finding a cloud of sediment instead. This discovery turned planetary science upside down. Traditional models suggested gas giants formed when solid cores, 10 times heavier than Earth, gathered enough gas to become massive. But Jupiter's fuzzy core throws that idea into question. Could its core have eroded over time, mixing with the surrounding hydrogen and helium, or was it never solid to begin with? Some theories propose that a colossal impact early in Jupiter's history shattered and scattered its core. Others argue the core might be dissolving slowly, like sugar in water, due to extreme pressures and temperatures. Whatever the explanation, this blurry boundary between core and atmosphere challenges our understanding of how planets, not just in our solar system, but across the universe, take shape. And if Jupiter doesn't play by the rules, what does that mean for the hundreds of gas giants we've spotted orbiting distant stars? The mystery of its missing core isn't just about Jupiter. It's rewriting the story of planetary birth itself. Now, shifting our gaze to another cosmic oddity, let's unravel the mystery of Jupiter's lopsided magnetic field. Unlike Earth's relatively balanced magnetic field, Jupiter's is strikingly uneven, far stronger in the north than in the south. This bizarre asymmetry defies everything we thought we knew about how planetary magnetic fields work. Typically, a planet's magnetic field is generated by the churning of conductive fluids deep inside its core, a process called the dynamo effect. Earth's dynamo is pretty symmetrical, giving us a magnetic field that's roughly uniform. But Jupiter's, it's like a magnet with one end cranked up to 11 while the other barely hums along. So, what's causing this imbalance? Scientists are stumped. One leading theory suggests that Jupiter's interior might be layered in a way we don't fully understand, perhaps with pockets of metallic hydrogen, the electrically conductive material thought to power its dynamo, distributed unevenly. Another idea is that the planet's rapid rotation, spinning once every 10 hours, somehow twists the magnetic field into this lopsided shape. Then there's the wild card, Jupiter's great blue spot, a concentrated patch of magnetic intensity near the equator that might be tugging the entire field out of whack. This magnetic oddity isn't just a curiosity, it's a window into Jupiter's hidden depths. The asymmetry hints at chaotic, turbulent processes happening deep inside the planet, where pressures and temperatures are so extreme that hydrogen acts like a liquid metal. If we can crack this puzzle, we might finally understand how gas giants generate their immense magnetic fields, which are hundreds of times stronger than Earth. And since Jupiter's magnetosphere is the largest structure in the solar system after the Sun itself, this isn't just about one planet, it's about how magnetic fields shape the environments of worlds far beyond our own. Up next, we'll explore another electrifying mystery, Jupiter's auroras, which outshine Earth's in ways that leave scientists utterly baffled. Now, let's turn our attention to one of the most dazzling spectacles in the solar system, Jupiter's auroras. These aren't just your ordinary northern and southern lights. Jupiter's auroras are colossal, unpredictable, and hundreds of times more energetic than Earth's, painting the planet's poles with otherworldly glows that leave scientists scratching their heads. Here's the twist. On Earth, auroras are powered by charged particles from the solar wind colliding with our atmosphere. But Jupiter's auroras don't play by those rules. Even when the solar wind is calm, Jupiter's lights rage on, brighter and fiercer than ever. So what's fueling them? The answer might lie in Jupiter's own backyard, its moons. Io, Europa, and Ganymede aren't just icy worlds, they're cosmic power stations. Io, the most volcanic object in the solar system, spews tons of sulfur and oxygen into space, while Europa and Ganymede leak water vapor from their subsurface oceans. Jupiter's monstrous magnetic field grabs these particles, accelerates them to insane speeds, and slams them into the planet's atmosphere, creating auroras that never fade. But the real mystery, these auroras don't just pulse, they explode in unpredictable bursts, sometimes flaring up in regions where they shouldn't exist at all. Scientists suspect Jupiter's magnetic field is playing a chaotic game of tug-of-war with its moons, creating electric currents that ignite these bizarre light shows. And here's the kicker, some of these auroras are so powerful, they generate X-rays, something Earth's lights could never do. Understanding Jupiter's auroras isn't just about pretty lights. It's a clue to how the planet's magnetic engine works, how its moons interact with it, and even how energy flows in extreme cosmic environments. Next up, we'll dive into another fiery puzzle, why Jupiter radiates more heat than it gets from the Sun. Now, let's tackle another burning question literally. Jupiter isn't just a giant ball of gas, it's a cosmic radiator pumping out more heat than it soaks up from the Sun. And that's weird. Planets usually cool down over time, but Jupiter, it's defying the rules, glowing with an inner fire that scientists are still struggling to explain. So where's all this extra heat coming from? One leading theory points to Jupiter's birth. When the planet formed, it was a swirling mess of gas and dust collapsing under its own gravity. That process generated immense heat that's still leaking out billions of years later. Think of it like a cosmic leftover, a slow release of energy from its chaotic beginnings. But here's the catch. Calculations suggest this alone shouldn't account for all the heat we're seeing. Enter helium rain. Deep inside Jupiter, where pressures are crushing, Helium might be doing something bizarre, separating from hydrogen and forming droplets that fall like rain. As these droplets sink, they release gravitational energy, heating up the planet from within. It's like Jupiter has its own internal furnace, stoked by this exotic weather. But wait, there's a wilder idea. Some scientists speculate that Jupiter's core could harbor trace amounts of radioactive elements or even, dare we say it, nuclear reactions. Not full-blown fusion like a star, but perhaps rare processes involving heavy elements like lithium or deuterium. It's a long shot, but if true, it would rewrite our understanding of how gas giants work. The puzzle deepens when you realize Jupiter's heat isn't uniform. Some regions radiate more than others, hinting at complex dynamics beneath those swirling clouds. Could there be layers of material churning in ways we don't yet understand, or hidden energy sources we haven't even imagined? One thing's clear: Jupiter's heat mystery isn't just about temperature. It's a window into the planet's hidden depths, its evolution, and maybe even the secrets of other gas giants across the cosmos. Up next, we'll peel back another layer of Jupiter's enigma, the strange striped patterns that wrap around its surface like a cosmic barcode. Now, shifting our gaze to Jupiter's stunning surface, we're met with a mesmerizing sight: those iconic stripes wrapping around the planet like a celestial fingerprint. These bands aren't just for show, they're the result of some of the most powerful jet streams in the solar system, racing at speeds of up to 300 miles per hour. But what's truly baffling is how these stripes stay so distinct, never blending together like Earth's weather systems. The secret lies in Jupiter's lack of a solid surface. On Earth, mountains and continents disrupt air currents, causing weather patterns to mix and evolve. But Jupiter's atmosphere is a deep, churning ocean of gas, with jet streams that carve out these bands like invisible knives. The lighter zones are where gas rises, while the darker belts are where it sinks, creating a pattern that's both beautiful and bizarrely stable, even more intriguing. These bands aren't just skin deep. Some plunge hundreds of miles into Jupiter's atmosphere, far deeper than scientists once thought, and their colors. That's another puzzle. The variations likely come from differences in cloud composition: ammonia ice in the white zones, deeper compounds like ammonium hydrosulfide in the browns and reds. But why they're so sharply separated with no messy gradients remains a mystery. Then there's the question of energy. Earth's jet streams are powered by sunlight and rotation, but Jupiter's stripes seem to draw energy from deep within the planet itself. Some researchers think heat rising from Jupiter's core fuels these winds, while others point to smaller eddies merging into larger currents. Either way, it's a system unlike anything we see on Earth or anywhere else in the solar system. What's clear is that these stripes are more than just decoration. They're a window into Jupiter's turbulent heart, revealing forces we're only beginning to understand. And as we peel back another layer of this gas giant's secrets, we're left with even bigger questions about what drives its wild, striped beauty. Up next, we'll venture to Jupiter's poles, where a cluster of cyclones defies everything we know about planetary weather. Now, let's turn our attention to one of Jupiter's most baffling discoveries: the strange, swirling cyclones clustered at its poles. When NASA Juno spacecraft first revealed these storms, scientists were stunned. Unlike anything seen on Earth or any other planet, these cyclones form intricate geometric patterns, with 8 storms circling a central one at the North Pole and 5 arranged in a pentagon at the south. And here's the real head-scratcher: they don't merge. Despite being packed tightly together, these cyclones have remained stable for years, defying every expectation of how polar weather should behave. What makes these storms even more puzzling is their temperature. Dubbed cold cyclones, they're actually warmer at their edges and cooler in the centers, the opposite of how storms typically behave on Earth. This bizarre thermal profile suggests there's something unusual about how energy moves through Jupiter's polar atmosphere. Some researchers think the planet's intense magnetic field might play a role, channeling energy in ways we don't yet understand. Others speculate that the cyclones might be rooted much deeper in Jupiter's atmosphere than we can currently observe, tapping into hidden heat sources. Then there's the question of their perfect arrangement. Why don't these cyclones collide or disrupt each other? On Earth, storms merge all the time, but Jupiter's polar cyclones seem to dance around one another in an endless, orderly waltz. One theory suggests that the storms might be surrounded by narrow bands of wind that act like barriers, keeping them separate. Another idea is that the cyclones are somehow feeding off each other's energy, maintaining a delicate balance that prevents them from merging. Whatever the explanation, these enigmatic storms are rewriting the rules of planetary weather. They're a reminder that Jupiter's poles are a world unto themselves, governed by forces we're only beginning to unravel. And as we continue to study these icy whirlwinds, they might just hold the key to understanding some of Jupiter's deepest atmospheric secrets. Next up, we'll dive into another mystery: why Jupiter's atmosphere seems to hold far more water than we ever expected. Shifting gears to another enigma, let's talk about Jupiter's water, or rather, the confusing lack of it where scientists expected to find plenty. When the Galileo probe plunged into Jupiter's atmosphere in 1995, it sent back data suggesting the planet was surprisingly dry, with far less water than predicted. This was a shock because Jupiter's position in the solar system and its role as a gas giant should have made it a water-rich world, packed with oxygen and hydrogen from the primordial solar nebula. For decades, this mystery lingered, leaving researchers scratching their heads. Then came Juno. A newer mission revealed something entirely different: pockets of Jupiter's atmosphere where water appears to be much more abundant, especially near the equator. This stark contradiction between the two datasets has sparked heated debates. Was Galileo's probe just unlucky, dropping into an unusually dry patch? Or is Jupiter's water unevenly distributed, hidden deep beneath layers of clouds where our instruments can't easily see it? The answer matters more than you might think. Water isn't just about weather, it's a cosmic clue. The amount of water in Jupiter's atmosphere could rewrite the story of how the planet formed. If Jupiter really is drier than expected, it might mean the solar system's building blocks weren't as water-rich as we assumed. Alternatively, if Juno's findings hold up, it could suggest Jupiter's water is trapped in a complex cycle, churning between its depths and upper atmosphere in ways we don't yet grasp. Some scientists even speculate that Jupiter's water might be locked away in exotic forms, like mushballs, slushy hailstones made of ammonia and water that sink into the planet's interior, hiding the true abundance from our probes. Others wonder if Jupiter's fierce storms are redistributing water in unpredictable patterns, creating dry zones and wet zones that defy simple explanations. One thing's clear: Jupiter's water mystery is far from solved, and until we send more missions or develop better tools to peer beneath its clouds, this puzzle will keep challenging our understanding of not just Jupiter, but the entire solar system's history. Up next, we'll explore another electrifying mystery: why Jupiter's lightning behaves so differently from Earth's. Now, let's turn our attention to something truly electrifying: Jupiter's lightning. If you thought Earth's thunderstorms were intense, wait until you hear about the bolts crackling across Jupiter's skies. Unlike our planet, where lightning strikes mostly near the equator, Jupiter's lightning has a peculiar preference for the polar regions. And it's not just the location that's odd. These bolts are far more frequent and pack a different kind of punch. On Earth, lightning is born from the friction of water droplets and ice crystals in storm clouds. But Jupiter's lightning seems to dance to a different tune. Scientists believe it's fueled by ammonia-rich clouds, where ammonia acts like an antifreeze, creating slushy mixtures that generate electrical charges in ways we're still trying to understand. This could explain why Jupiter's lightning is so much more common, up to 3 times as frequent as Earth's. and why it favors the colder polar zones where these exotic cloud layers thrive. What's even stranger is the depth of these strikes. While Earth's lightning flashes in the lower atmosphere, Jupiter's bolts appear to originate much deeper, where pressures and temperatures are extreme. Some bolts even seem to climb upward, defying expectations. This bizarre behavior hints at a chaotic, layered atmosphere where chemicals like ammonia and water interact in ways we've never seen before. So why does this matter? Lightning isn't just a light show. It's a window into a planet's hidden chemistry. The way Jupiter's lightning behaves tells us about the ingredients swirling in its clouds and how energy moves through its atmosphere. It might even help explain why Jupiter's weather is so wildly different from ours. But the biggest mystery remains: why are these bolts so drawn to the poles? Some theories suggest Jupiter's powerful magnetic field funnels energy there, while others point to unique storm systems that brew in the cold. Whatever the reason, one thing's certain: Jupiter's lightning is rewriting the rulebook on how planetary storms work. And as we keep studying it, we're not just learning about Jupiter, we're uncovering secrets about how all gas giants, including those beyond our solar system, might behave. Next up, we'll dive into another head-scratcher: why Jupiter's atmosphere holds a surprising abundance of heavy elements, and what that tells us about the planet's violent past. Now, here's something that might catch you off guard. Jupiter's atmosphere is packed with heavy elements like carbon and nitrogen, but they're oddly diluted. You'd expect a gas giant to be mostly hydrogen and helium, right? Yet, Jupiter's air holds traces of these heavier ingredients in amounts that don't quite add up. So where did they come from? One leading theory points to Jupiter's violent past. Imagine comets and asteroids rich in these elements, smashing into the planet over billions of years. Each impact could have delivered a sprinkle of heavy material, slowly building up the concentrations we see today. But here's the twist: some scientists argue there's too much of these elements for that to be the only explanation. Another possibility takes us back to the very birth of the solar system. Jupiter might have formed from a pocket of the primordial solar nebula that was already laced with these heavier compounds. As the planet grew, it could have trapped them in its atmosphere, preserving a chemical fingerprint of the early universe. But why does this matter? These elements are like cosmic breadcrumbs. By studying their ratios, how much carbon there is compared to nitrogen, for example, we can piece together Jupiter's origin story. Did it form closer to the Sun, where heavier elements were more common, or farther out, where they were scarce? The answers could rewrite our understanding of how gas giants are born. And here's the real kicker: Jupiter's heavy elements might not be evenly mixed. Some layers of its atmosphere could hold higher concentrations, creating invisible chemical boundaries that influence everything from storms to heat flow. It's another reminder that Jupiter, for all its size, is a planet of delicate balances and hidden surprises. Up next, we'll probe another enigma: just how deep does Jupiter's atmosphere go, and why do the latest measurements leave scientists scratching their heads? Now let's dive deeper, literally into one of Jupiter's most baffling layers, its atmosphere. Just how far down does it stretch? For years, scientists assumed Jupiter's swirling clouds and storms were just skin deep, a relatively thin veneer over a more uniform interior. But thanks to the Juno mission, we now know that's far from the truth. Juno's gravity measurements revealed something startling: Jupiter's atmosphere isn't just a shallow blanket. It plunges thousands of kilometers deep, blending gradually into the planet's liquid metallic hydrogen core. This discovery turned old assumptions upside down. Earlier models suggested the atmosphere might only extend a few hundred kilometers before giving way to denser layers. But Juno's data showed the weather layer, where storms like the Great Red Spot rage, could go as deep as 3,000 kilometers, or about 1/10 of Jupiter's radius. Why does this matter? Because depth changes everything. A deeper atmosphere means Jupiter's iconic bands and jet streams aren't just surface-level features. they're rooted far below, driven by processes we can't yet see. It also means the planet's interior is far more dynamic than we thought, with heat and materials circulating over vast distances. But here's the real puzzle. If the atmosphere runs so deep, why doesn't it mix more? On Earth, deep oceans or air currents tend to even things out over time. Yet Jupiter's bands stay sharply defined, as if some invisible barrier keeps them separate. Some researchers think powerful magnetic fields or rotating layers of different densities might be at play, but no one knows for sure. And then there's the heat. A deeper atmosphere could help explain why Jupiter radiates more energy than it gets from the Sun. Hidden currents might be transporting heat from the core upward in ways we don't yet understand. Every new layer Juno uncovers seems to add more questions than answers. Up next, we'll tackle another head-scratcher: why Jupiter's rotation rates aren't consistent, and how the planet manages to hold itself together despite the chaos. Now let's spin into another one of Jupiter's quirks: its inconsistent rotation rates. Unlike Earth, where the entire planet spins as a solid block, Jupiter's atmosphere dances to its own chaotic rhythm. At the equator, clouds race around the planet at speeds of nearly 430 kilometers per hour, completing a full rotation in just under 10 hours. But head toward the poles and things slow down dramatically, adding an extra 5 minutes or more to that rotation time. This bizarre phenomenon, called differential rotation, is something you'd expect to tear a planet apart. Yet Jupiter holds itself together, and scientists are still piecing together how. One key factor: Jupiter isn't a solid ball. It's a swirling ocean of gas and liquid metallic hydrogen, with no rigid surface to resist these mismatched speeds. The planet's immense gravity and internal pressures act like cosmic glue, keeping everything bound together despite the turbulence. But here's where it gets even stranger. Jupiter's jet streams, those high-speed bands of wind separating its colorful stripes, play a starring role in this rotation puzzle. These jet streams flow east or west, creating a tug-of-war between latitudes. Some researchers think deep-seated magnetic fields or heat-driven currents might be orchestrating this chaos, but the exact mechanism remains elusive. What's clear is that Jupiter's rotation isn't just a curiosity, it's a window into the planet's hidden depths. The way these layers interact could reveal secrets about how gas giants form and evolve. And while Earth's steady spin keeps our days predictable, Jupiter's wild, uneven whirl reminds us just how alien some worlds can be. Coming up, we'll unravel another mystery: how Jupiter's faint, dusty rings defy expectations and what keeps them from fading away. Now let's shift our gaze to something far more delicate: Jupiter's rings. Unlike Saturn's dazzling, icy hoops, Jupiter's rings are faint, dusty, and almost ghostly in comparison. But don't let their subtle appearance fool you. These rings hold secrets just as intriguing as their flashy neighbors. The mystery begins with their origin. Jupiter's rings aren't made of pristine ice like Saturn's. Instead, they're composed of tiny, dark particles, likely dust kicked up by micrometeoroids slamming into the planet's small inner moons like Metis and Adrastea. Every time these space rocks collide with the moons, they send debris flying into orbit, creating a constant, if faint, replenishment of the ring material. What's fascinating is how these rings manage to persist. Without a steady supply of new dust, Jupiter's rings would vanish over time, pulled apart by the planet's gravity or eroded by radiation. But the moons act like invisible gardeners tending to this cosmic debris field. Scientists suspect similar processes might be at work around other gas giants, but Jupiter's rings are unique in their delicate balance. And here's another twist: Jupiter's rings aren't just one uniform band. They're divided into distinct sections, including a gossamer, thin outer ring that stretches far beyond the main structure. This outer ring might owe its existence to even more distant moons like Thebe and Amalthea, whose orbits help shepherd the dust into place. So why don't Jupiter's rings shine like Saturn's? The answer lies in their composition. Saturn's rings are mostly ice reflecting sunlight brilliantly. Jupiter's, on the other hand, are made of darker, rockier material, absorbing light rather than bouncing it back. It's a subtle difference, but one that speaks volumes about how diverse planetary rings can be. Up next, we'll explore another cosmic oddity, the uneven distribution of Trojan asteroids in Jupiter's orbit, and why one group outnumbers the other. Now, let's turn our attention to a cosmic traffic jam unlike any other Jupiter's Trojan asteroids. These rocky hitchhikers share the planet's orbit, but here's the catch: they're not evenly distributed. In fact, one group, nicknamed the Greeks, significantly outnumbers their counterparts, the Trojans. Why this imbalance exists is one of Jupiter's most puzzling mysteries. These asteroids aren't just random space rocks, they're trapped in gravitational sweet spots called Lagrange points, where Jupiter's pull and the Sun's gravity balance perfectly. The Greeks cluster ahead of Jupiter while the Trojans trail behind, but observations reveal something odd. The Greeks outnumber the Trojans by a noticeable margin. Scientists have scratched their heads over this for decades. One theory suggests it's a relic of the solar system's chaotic early days. Jupiter's migration, a slow drift inward or outward, could have disrupted the Trojans more than the Greeks, thinning their ranks. Another idea points to collisions. Maybe the Trojans experienced more destructive crashes over billions of years, leaving fewer survivors. Or perhaps it's a quirk of observation. Some Trojans might be darker or harder to spot, making them seem rarer than they are. This imbalance isn't just a curiosity, it's a clue. If the Greeks really are more numerous, it could mean Jupiter's orbit wasn't always so stable. Or it might hint at unseen forces like past encounters with other giant planets. Either way, these asteroids are like fossils, preserving secrets about Jupiter's turbulent history. Next up, we'll venture into Jupiter's ethereal outer rings, where faint, almost invisible structures defy expectations in ways that might just rewrite what we know about planetary rings. Now let's drift beyond Jupiter's main ring and into the ghostly realm of its gossamer rings. Unlike Saturn's bold, icy rings, Jupiter's outermost rings are so faint and wispy, they're almost invisible, more like a cosmic whisper than a declaration. These ethereal structures, named for their delicate appearance, are made of fine dust particles, so sparse that sunlight passes right through them. But don't let their subtlety fool you, their mystery runs deep. Scientists believe these gossamer rings owe their existence to Jupiter's tiny moons, Thebe and Amalthea. As micrometeoroids pummel these moons, they kick up dust, which then drifts into orbit around Jupiter. But here's the puzzle. Why are these rings so staggeringly diffuse? On Earth, dust settles quickly, yet Jupiter's gossamer rings persist, stretching thousands of miles into space. One theory suggests Jupiter's powerful magnetic field plays a role, gently shepherding the dust particles and preventing them from clumping together. Another idea points to the planet's intense radiation belts, which might electrically charge the dust, causing it to repel itself and stay spread out. What's even stranger is how these rings defy expectations. Most planetary rings have clear edges, but Jupiter's gossamer rings blur into space, fading gradually until they vanish. Some researchers think this could hint at unseen moons or even hidden gravitational nudges we haven't detected yet. Others propose that the rings are younger than we assumed, constantly replenished by fresh impacts on Thebe and Amalthea. These ghostly rings are more than just a celestial curiosity. They're a window into the delicate balance of forces shaping Jupiter's environment. And as we peel back their secrets, we might just uncover new clues about how all planetary rings form and evolve. Next, we'll step into the shadows, literally where Jupiter's eclipses do the opposite of what you'd expect, heating up the planet instead of cooling it down. Now let's venture into one of Jupiter's most baffling quirks, the so-called hot shadows phenomenon. Picture this: when one of Jupiter's moons casts a shadow on the planet's swirling atmosphere, you'd expect that patch to cool down, right? After all, that's how shadows work on Earth. But Jupiter loves to defy logic. Instead of cooling, these shadowed regions actually heat up, sometimes by as much as several hundred degrees. It's as if stepping into shade on a sunny day suddenly made you feel hotter, utterly counterintuitive. So, what's behind this cosmic contradiction? Scientists have a few compelling theories. One idea centers on Jupiter's wild winds. The planet's atmosphere is a churning maelstrom of jet streams and storms, and when a shadow temporarily blocks sunlight, it disrupts the usual energy flow. This disruption might trigger waves in the atmosphere, like ripples in a pond, which then compress and heat the gas as they travel. Think of it like squeezing a balloon. The pressure builds, and so does the temperature. Another theory points to Jupiter's intense magnetic field. The shadowed regions might experience a sudden drop in ionized particles, which normally help radiate heat away. With that cooling mechanism interrupted, the trapped heat has nowhere to go, causing temperatures to spike. It's like turning off a fan in a stuffy room. The heat just lingers. But here's the real head-scratcher. This effect isn't uniform. Some shadows cause dramatic heating, while others barely make a dent. That inconsistency suggests there's more to the story, perhaps involving hidden layers of Jupiter's atmosphere or interactions we haven't even discovered yet. This bizarre warming effect isn't just a curiosity, it's a clue. By studying these hot shadows, scientists hope to unravel deeper mysteries about how energy moves through Jupiter's atmosphere, and maybe even how gas giants across the universe behave. Up next, we'll turn our attention to another atmospheric oddity, Jupiter's white ovals, those enigmatic storms that come and go like cosmic ghosts. Now, shifting our gaze to another atmospheric marvel, let's unravel the mystery of Jupiter's white ovals. These sprawling, high-pressure storms are like the Great Red Spot's elusive cousins, just as fascinating but far more unpredictable. While the Great Red Spot has dominated Jupiter's skies for centuries, white ovals come and go, sometimes lasting decades before vanishing or merging with other storms. What makes these ovals so fleeting? For starters, they're not as deep or as energetically charged as the Great Red Spot. Think of them as towering clouds of ammonia ice, riding high in Jupiter's atmosphere, where they're more vulnerable to the planet's chaotic winds. Unlike the Great Red Spot, which seems to tap into some hidden energy source deep below, white ovals lack that same stability. They're like temporary whirlpools in a fast-moving river, easily disrupted by the currents around them. But here's where it gets even stranger. Some white ovals don't just fade away, they collide. When two of these storms meet, they can merge into a single, larger oval, or sometimes they just disappear. Scientists suspect these mergers might be key to understanding why some storms persist while others vanish. It's as if Jupiter's atmosphere is playing a cosmic game of survival where only the strongest storms endure. And then there's the color. Unlike the Great Red Spot's rusty hue, white ovals live up to their name, pale and ghostly. This likely comes from their composition. Ammonia ice crystals reflecting sunlight, with fewer of the complex chemicals that give the Great Red Spot its signature tint. But why don't they darken or change over time? That's another puzzle waiting to be solved. What's clear is that these ovals are more than just weather quirks. They're windows into the turbulent dynamics of Jupiter's atmosphere, showing us how energy swirls, clashes, and dissipates on a scale we can barely imagine. Up next, we'll dive into the chaos of Jupiter's magnetosphere, where magnetic fields and solar winds collide in a spectacle unlike anything in our solar system. Now, let's venture into the swirling chaos of Jupiter's magnetosphere, a realm where the planet's colossal magnetic field battles the solar wind in a never-ending cosmic tug-of-war. Unlike Earth's relatively orderly magnetosphere, Jupiter's is a maelstrom of unpredictability, stretching millions of miles into space and behaving more like a living, breathing entity than a static shield. At the heart of this chaos is Jupiter's magnetic field, the strongest in the solar system after the Sun's. It's so powerful that if it were visible to the naked eye, it would appear larger than the full moon in our sky. But here's the twist: this field isn't symmetrical. It's lopsided, tangled, and constantly shifting, thanks to the planet's rapid rotation and the turbulent metallic hydrogen deep within its interior. When the solar wind, a stream of charged particles from the sun, slams into this magnetic chaos, it doesn't just deflect smoothly. Instead, it triggers violent disturbances, creating shock waves and turbulence that ripple across the magnetosphere. One of the most baffling features of this system is the flux tube, a twisting, snake-like structure made of charged particles that connects Jupiter to its moons, particularly volcanic Io. These tubes are like electrical highways, funneling energy back and forth in ways scientists still don't fully understand. Sometimes they flicker unpredictably, vanishing and reappearing without warning. Other times, they grow so intense they generate radio bursts detectable from Earth. It's as if Jupiter's magnetosphere has a mind of its own, rewriting the rules of physics as we know them. What's even more astonishing is how this magnetosphere interacts with Jupiter's auroras. While Earth's auroras are driven by solar wind, Jupiter's are powered by its own magnetic chaos, with particles spiraling along field lines and colliding in dazzling, erratic displays. These auroras don't just pulse, they rage, covering areas larger than our entire planet and flaring up in ways that defy prediction. The takeaway: Jupiter's magnetosphere isn't just chaotic, it's a laboratory of extreme space weather, challenging everything we thought we knew about magnetic fields. Up next, we'll tune into the odd radio emissions leaking from this planetary powerhouse, signals so intense they outshine every other planet in the solar system. Now, let's tune into one of Jupiter's most bizarre symphonies, the odd radio emissions that crackle through space like a cosmic radio station gone wild. These aren't your typical signals. Jupiter's radio bursts are sporadic, deafeningly powerful, and unlike anything else in the solar system. Imagine turning a dial and suddenly hearing static so loud it drowns out every other planet's whispers. That's Jupiter for you, a planetary DJ blasting beats no one can ignore. So, what's behind these electrifying performances? It all ties back to Jupiter's chaotic magnetosphere. As charged particles spiral along the planet's lopsided magnetic field lines, they accelerate to near light speeds, releasing energy as intense radio waves. But here's the kicker: these bursts aren't steady. They come in unpredictable flares, often linked to the planet's volcanic moon, Io. When Io's eruptions spew charged particles into Jupiter's magnetic grip, it's like throwing gasoline on a fire. The resulting radio storms can outshine the sun in certain frequencies. What really stumps scientists is the sheer intensity. Jupiter's radio emissions are thousands of times stronger than Earth's, and they pulse in patterns that defy easy explanation. Some bursts last minutes, others hours, with no clear rhythm or reason. It's as if Jupiter is sending coded messages we're only beginning to decode. And here's the cosmic irony: these radio waves aren't just noise. They're a window into Jupiter's hidden depths, revealing how its magnetic field twists, snaps, and reconnects in real time. Every burst is a clue, a piece of the puzzle in understanding how gas giants harness and unleash energy on a scale we can barely fathom. Next up, we'll peer into the shadows of Jupiter's polar regions, where darkness holds secrets even light can't reveal. But let's shift our gaze from Jupiter's roaring radio storms to something far more subtle yet just as puzzling. The planet's polar regions don't just hide in shadow, they defy expectations by appearing eerily dark in certain wavelengths of light. Unlike the vibrant bands and swirling storms that dominate Jupiter's lower latitudes, the poles seem to swallow light, leaving scientists scratching their heads. So, what's casting this cosmic shade? One leading theory points to a cocktail of exotic chemicals lurking in Jupiter's upper atmosphere. When viewed in infrared or ultraviolet, the poles absorb light instead of reflecting it, suggesting a dense layer of haze or particles unlike anything found elsewhere on the planet. Some researchers suspect hydrocarbons molecules like acetylene or ethane could be forming a dark, sooty blanket. Others propose that charged particles funneled by Jupiter's magnetic field are smearing the poles with compounds we've yet to identify. Then there's the wild card, atmospheric dynamics. Jupiter's poles are a battleground of swirling cyclones, but unlike Earth's polar vortices, these storms might be dredging up material from deep below. Imagine a celestial blender churning up dark, heavy molecules from the planet's depths and painting them across the poles. Or perhaps the lack of sunlight at these high latitudes triggers chemical reactions that create these shadowy tints. The real mystery, this darkness isn't uniform. Juno's close-up shots reveal patchy, mottled patterns, like a cosmic inkblot test with no clear answer. Whether it's chemistry, weather, or some interplay of both, Jupiter's dark poles remind us that even the most advanced telescopes can't always pierce the secrets of a gas giant's shadowy corners. Now prepare to witness another electrifying enigma, Jupiter's shallow lightning, where storms don't play by Earth's rules. Now, let's crack open another bizarre twist in Jupiter's stormy playbook, lightning that doesn't strike where you'd expect. Forget the deep, rumbling bolts we see on Earth. Jupiter's got something far stranger, shallow lightning. These aren't your typical sky-splitting strikes. Instead, they flicker high in the atmosphere, inside fluffy clouds of ammonia and water, earning them the nickname mushballs. So why does lightning act so differently here? On Earth, lightning forms deep in storm clouds where water droplets and ice collide, building up electric charge. But Jupiter's shallow lightning happens way higher up, where temperatures are freezing and ammonia acts like an antifreeze, mixing with water to create a slushy, electrically charged soup. When this sloshy mess gets turbulent, zap, you get a flicker of lightning that's weaker but way weirder than anything on our planet. What's even wilder is what these mushy bolts reveal about Jupiter's hidden layers. Scientists think these shallow storms are dredging up ammonia from deep below, redistributing it across the atmosphere like a cosmic conveyor belt. That could explain why some parts of Jupiter's upper clouds are richer in ammonia than others. It's all getting stirred up by these high-altitude electrical tantrums. But here's the real head-scratcher. Some of these mushballs might actually fall. Imagine hailstones, but made of ammonia-rich slush tumbling down into Jupiter's depths. That could be why certain regions seem to run out of ammonia. It's getting dragged below by these bizarre, stormy deliveries. Jupiter's shallow lightning isn't just a curiosity. It's a window into the gas giant's churning, chaotic heart. And just when we think we've got it figured out, the next mystery flares up. Speaking of flares, wait until you hear about the planet's unexplained flashes bright enough to spot from Earth, but with origins that still leave scientists in the dark. Now, shifting our gaze to another electrifying phenomenon, Jupiter's mystery flashes. These aren't your average lightning strikes or auroras. Picture this: sudden, brilliant bursts of light flickering in Jupiter's thick atmosphere, bright enough to be spotted by telescopes right here on Earth. What's causing these dazzling flares? The leading theory points to cosmic visitors, asteroids or comets slamming into Jupiter at incredible speeds, vaporizing on impact and releasing a blinding flash of energy. But here's the puzzling part. These flashes don't always leave behind the clues scientists expect. On Earth, a meteor impact might carve out a crater or scatter debris, making it easy to trace. Jupiter, though, swallows the evidence whole. Its dense, turbulent atmosphere quickly churns away any visible scars, leaving researchers with little more than a fleeting glow to study. That's why even the most powerful telescopes struggle to pin down exactly how often these impacts happen, or what kind of objects are causing them. Some estimates suggest Jupiter gets hit by space rocks as big as a football field several times a year, while smaller impacts might occur monthly. But without consistent observations, it's like trying to count fireflies in a storm, and the stakes are higher than you might think. Studying these flashes isn't just about Jupiter. It's a window into the chaotic traffic of asteroids and comets lurking in our solar system. Every impact helps scientists gauge how much debris is hurtling around out there and how often Earth might face similar threats. Yet, for all their brilliance, these flashes remain frustratingly elusive. Are they always from impacts, or could some be triggered by deep atmospheric upheavals we don't yet understand? The more we watch, the more questions arise. And just like that, Jupiter turns another flash of light into a shadow of mystery. Up next, we'll dive into something even stealthier: storms that rage invisibly, hidden from even the sharpest lenses. Just when you thought Jupiter couldn't get any stranger, let's peel back another layer of its secrets: storms that rage in plain sight, yet remain completely invisible. These aren't your typical swirling tempests like the Great Red Spot. No, these are stealth storms detected only by specialized instruments while optical telescopes see nothing. How can a storm powerful enough to churn Jupiter's atmosphere simply vanish from view? The answer lies in what these storms are made of. Most of Jupiter's visible clouds reflect sunlight thanks to ammonia crystals and other reflective particles. But stealth storms seem to lack these shiny ingredients. Instead, they might be packed with darker, more absorbent materials like complex hydrocarbons or even exotic compounds we haven't identified yet. Imagine a storm so dense with dark matter that it swallows light instead of bouncing it back, blending into the planet's shadowy depths like a cosmic ninja. But here's the real head-scratcher. Why don't these storms mix with the brighter clouds around them? Jupiter's atmosphere is a chaotic blender of gases, yet these stealthy tempests maintain their eerie invisibility. Some scientists suspect they're trapped in deeper layers where sunlight can't reach, or that they form under conditions so unique they defy our current models of planetary weather. What's wild is that these storms aren't rare anomalies. They might be everywhere, hidden in plain sight. Without instruments like microwave or infrared detectors, we'd never know they existed. And that raises a tantalizing question: how much of Jupiter's fury are we still missing? Every time we think we've mapped its chaos, the planet reminds us some of its best tricks are the ones we can't even see. Now, let's turn our attention to something equally mesmerizing but far more delicate: the bizarre, thread-like filaments weaving through Jupiter's clouds, as if the planet itself is stitching its own atmospheric tapestry. Now, shifting our gaze to something almost artistic in Jupiter's chaotic skies, we find these mesmerizing, thread-like filaments weaving through the clouds. Picture delicate strands of silk stretched across a canvas of storms, defying the planet's brutal winds. How can something so fragile-looking survive in an atmosphere where hurricanes rage for centuries? These folded filament structures are unlike anything else in our solar system. Some stretch for thousands of miles, curling and twisting like cosmic calligraphy. Scientists believe they're made of denser, cooler material than the surrounding clouds, possibly ammonia or water vapor frozen into intricate ribbons. But here's the puzzle. Jupiter's winds scream at speeds over 300 miles per hour, enough to shred Earth's strongest storms to pieces. Yet these filaments hold their shape, sometimes for months or even years. One theory suggests they're anchored by powerful, hidden currents deep in Jupiter's atmosphere, like invisible hands guiding the threads into place. Others think they might be the scars of colossal collisions between storm systems, frozen in time as the planet's winds sculpt them into these eerie patterns. And then there's the wild-card idea that these filaments are actually signs of towering, vertical winds we can't yet measure, stitching the clouds together from above and below. What's truly mind-bending is that these structures aren't random. They often appear in clusters, forming geometric networks that look almost intentional. It's as if Jupiter has its own atmospheric embroidery, a hidden language written in storms. Every time we spot these filaments, they challenge our understanding of fluid dynamics on a planetary scale. If something so delicate can thrive in this gas giant's fury, what other impossibilities are we just beginning to uncover? And speaking of impossibilities, let's dive into another head-scratcher. Those strange bumps in Jupiter's gravity data that hint at secrets buried deep beneath the clouds. Now, let's peel back another layer of Jupiter's enigma, those baffling bumps in its gravity data. When NASA Juno spacecraft mapped the planet's gravitational field, scientists expected smooth, predictable patterns. Instead, they found odd, localized spikes and dips, like invisible speed bumps buried deep beneath the clouds. These anomalies suggest something massive and mysterious is lurking inside Jupiter, warping gravity in ways we can't yet fully explain. One leading theory points to dense, swirling layers of metallic hydrogen, a form of hydrogen so compressed it behaves like a liquid metal. These layers might be unevenly distributed, creating pockets of extra mass that tug on Juno as it orbits. But here's the twist. Some of these gravity bumps don't align with Jupiter's visible features, like storms or jet streams. That means whatever's causing them is hidden far below the chaos we can see, possibly thousands of miles deep. Then there's the wilder idea, exotic matter. Some researchers speculate that Jupiter's core might contain strange, high-pressure forms of matter unlike anything on Earth. Imagine materials so dense they defy our current physics, or even remnants of the planet's violent formation, frozen in time. Others propose that these bumps could be the fingerprints of ancient, swallowed-up moons or planetary fragments, now dissolved into Jupiter's interior. What makes this puzzle even more intriguing is that these gravity anomalies aren't static. They shift over time, hinting that Jupiter's insides are anything but calm. It's as if the planet has a hidden heartbeat, pulsing with currents and collisions we're only beginning to detect. Every new Juno flyby adds another piece to the puzzle, but for now, these gravity bumps remain one of Jupiter's most tantalizing secrets, proof that even after centuries of study, the King of Planets still has stories left to tell. And just when you think Jupiter couldn't get any stranger, wait until you hear about its polar regions, where darkness holds clues to yet another mystery. As we wrap up this journey through Jupiter's greatest enigmas, it's astonishing to realize just how much remains hidden beneath those swirling clouds. From the great red spot's endless storm to the bizarre gravity bumps deep within its core, each mystery peels back another layer of this gas giant's secrets. We've explored the lopsided magnetic field, the polar cyclones that refuse to merge, and the lightning that defies earthly logic, yet every answer seems to lead to even bigger questions. Jupiter isn't just a planet, it's a cosmic puzzle box challenging everything we think we know about planetary science. And while missions like Juno have given us unprecedented glimpses, the truth is we've barely scratched the surface. That's where you come in. The next chapter of discovery is already being written, with missions like Europa Clipper and JUICE set to unveil even more of Jupiter's secrets in the coming years. So stay curious, keep looking up, and remember the universe's greatest stories are still being told. If you're as fascinated by these mysteries as we are, hit that subscribe button and ring the notification bell so you won't miss our next deep dive into the wonders of space. Until then, keep wondering, keep exploring, and who knows, maybe one day you'll help solve one of Jupiter's riddles yourself.